really happy about this opportunity. Good evening, everyone. And yeah, this opportunity to finally catch up with some of the later trends and developments in image processing. Why don't I promise you the latest trends and developments? There are a lot of things happening, and they are happening fast. And in my 20 minutes, I would just like to focus on a very interesting aspect, at least to me interesting. I hope you'll find it quite interesting too. So it will be no less than the unification of language and image processing on the other hand. It will be mostly from an academic point of view, but I'd be very interested in your thoughts on how this could be applied also to industrial standards and in what direction we can go. All right, so let's start. In case you're not already fed up with ChatGPT screenshots, here is another one. I think still this is quite interesting because, it's an impressive result on the one hand. On the other hand, it just visualizes very nicely what I want to bring across here. So I just uploaded one of the very specific images you see here in the left of the slide. And without any context, GPT tells me what's on the image, that this is a top view of a bottle. So that works really nice, even though this is very special or specific image content. Then I can ask it the question, is there any damage to the bottle? And again, accurately, it answers that there seems to be something chipped off. On the other hand, if I upload a good picture of a bottle, there is no damage spotted. Right. So it's already happening to some degree. And the reason is GPT stands for Generative Pre-trained Transformer. Generative because it produces text, pre-trained because it's been pre-trained on probably something like 1 trillion of words, at least if we're talking about GPT-3. And the last point, the last letter will be the most important for this session, which is transformer. So what are transformers and how are they different from the architectures we are using so far right now? So, and for that, just a quick recap about what we did in the past decade, roughly. We were just getting used to it. You've seen some nice applications of it. So when we were talking about AI and image processing, we were mainly talking about convolutional neural networks. And as Arvid showed us with a few examples now in the past sessions, we have some nice use cases we can cover with that, where convolutional neural networks really excel, like classification, object detection, semantic segmentation. There are extensions architectures which are transformers, which will be very interesting, I think, in the future. So this will be the rough outline of the talk. First of all, let's stick with what we know, convolutional neural networks. How do they extract information from images? Just to illustrate that a little bit better, just imagine that on this slide now, there is an image covered up, and I'll just reveal to you 2 pixels, and one of them belonged to an apple and the other one belonged to a tree. So if I ask you which pixel belongs to which object, it might be very hard for you to distinguish. And the reason is you're probably lacking context. As humans, we don't watch an image, a picture, and see 1 million pixels. But what we see is very intuitively the many and difficult correlations and relations between the pixels. So what we need to make this decision is we need context. So if I uncover a little bit of the neighborhood of each pixel, we can see that clearly, it starts to get at least a little bit clear that on the left side, I think, there the pixel belongs to an apple because we have these apple-like features in the image, and the other pixel seems to belong to a leaf. And if we increase the context, we can make this decision even more clear. We don't even need the full image now to make the decision. And at least for this very specialized task now. So this is how convolutional neural networks in very basic words work. They have this hierarchical information they extract from images, and they assume, or for convolutional neural networks, we assume that close pixels in the close neighborhood are always more important to a certain point in the image than far away pixels. So that means that, for example, if I want to identify the image, the pixel of an apple, the pixel next to it is probably most important, and the one in the upper right corner, probably not so much. So we have this hierarchical processing, which works quite nicely and which has been a very successful concept for the past decade. So what could we solve with that? Just as Arvid showed before, we have several use cases like classification, where we make image level decisions. There is an apple on that image. We have object detection, where we can localize and identify multiple objects, draw these bounding boxes around them. And we have semantic segmentation, where each and every pixel is assigned to a certain object. So we were just getting used to it, and this was what we were talking about when we were talking about AI. But then there came the transformers, and this is what I want to show with this slide. So you see by the arrow that in October 2020, for the first time, a so-called transformer architecture, also in the field of image processing, in vision field, first outperformed our good old convolutional neural networks. And it was reported in the publication that I've shown you on the slide. It's called An Image is Worth 16 times 16 Words. And what you can see from that is that there's already some sort of connection between words and images, language and images. And from this point on, if you follow the graph towards 2023, these transformer architectures have become more and more, increasingly more popular, while the popularity of the convolutional neural networks just starts slowly to decline, at least in academic papers. So that doesn't mean we're already in industry, but this is what seems to be now the main motivation in the research field. So what are these transformers then? And to explain that, to illustrate that a little bit better, I would like to go back to the roots of transformer architectures, which is in natural language processing. And for that, I would like you to have a look at these two sentences I'm showing you. The giraffe doesn't fit the suitcase because it is too small. And the other one, the giraffe doesn't fit the suitcase because it is too big. So basically, we have two identical sentences, and just one tiny little word has changed in the very end of the sentence, small, big. And as you might notice, in the first sentence, the word small refers to the suitcase. And in the second sentence, it refers to the word giraffe. So there are no grammatical rules that tell us this context, but we need semantic context for that. And just because suitcase is closer in the sentence to the word small doesn't mean it's more important, because in the second sentence, big refers to giraffe. So this rule of closely neighboring objects are more important to each other. This does not hold so well for natural language processing. Here, a different technique is used, and this has been published in a few years before that. And the paper was called "Attention is All You Need." And accordingly, the mechanism we use here to extract that context from language data is called attention, or self-attention in that case. So on a very high-level principle, we can now extract all the words from the upper sentence, for example, and I've just put a few here, and we write them down as sort of a table where we have in the rows, we have all the words, giraffe, suitcase, it, big. On the horizontal, we have the same words just again. And now we are querying for each word, how important are the other words? So most cases, each word is most important to itself. As we can see here, giraffe is most important for giraffe. It has the highest attention weight. But we continue doing this. And as you can see that the word it has a very strong relation to giraffe, but not so much of a relation to suitcase, because in this sentence, it refers to the giraffe and not to the suitcase. And if we continue this, we can come up with such a matrix that tells us which words are most related to which others. And as you can see that each words are equal here. So it doesn't matter how close the words are located, they're just all equal. Every word can be related with every other word. And this can be, for example, interesting if we want to translate something. If we want to translate that sentence to German, we can see that on the left-hand side, we would translate the it as sie, because, as we can see from the matrix, it refers to the giraffe, which is German female, die Giraffe. On the other hand, we would, on the right-hand side, we would translate it as er, because it refers to suitcase, which is in German male, der Koffer. So these attentions make a lot of a difference. And this is all within the context. So how can we now transfer this concept to images? We have been looking at these sentences now. The interesting thing is that with this new kind of architectures, we can transfer exactly the same principle also to image processing. And this has been proposed in this paper I've cited here. An image is worth 16 times 16 words. So how is that done? Well, first of all, we have to divide the image into patches. In our case, it's 4 times 4. In the paper, it is 16 times 16. So this is just for simplification. And now we have a way, or there is a way to encode these patches and treat them exactly like we treated words before. So each patch can be related through this attention mechanism with each other patch in the image. Doesn't matter how far it is away. So by losing this bias of saying closely located pixels have a stronger relation with each other, we can extract more complex relations in the image, more long-range relations. Because, I mean, it's clear that certain patches belong to the giraffe, but there's a lot of other interesting things happening in the background because, I mean, the giraffe has a spacesuit and there are dinosaurs in the background. What's happening here? And this is all important information, but it's all long-range information. So this is what transformers really excel at. They have a global understanding of the image. And this can now be expanded to some new use cases. For example, question answering, visual question answering, which I've already shown. This was the example which I've shown just in the beginning, which extends kind of the classification use case. So we can extract more information, more rich context of an image. We can interact with the image. And the most interesting thing about the use cases on the right-hand side is we unify here information from language and from images. And each time when we go from the left side to the right side, we open up to the whole word. So before that, everything we had to train in the neural network had to be explicitly present in the data. And now we can even make predictions about objects that had not explicitly been trained. This is very interesting. So I would like to explain this by showing the next, so basically the extension of the object detection, the open set object detection. And that means what I just said. We don't have to explicitly train objects, but we can also extract objects that we have not had in the data set. And we do this, as I said before, by combining the information we can extract from language with the information we can extract from images. We can, thanks to transformer models, treat them very similarly. we can basically encode them just as a bunch of numbers, simply spoken, and fuse the two. And then we can not only look at the self-attention, but we can also look at this cross-attention between the images on the on the vertical row, with the language side on the horizontal. And yeah, there we can extract all sorts of information that is encoded in the language. And by this, we can even go further than all the objects we explicitly trained in the data. So what we know so far is supervised training. Supervised means you train an object detection model, you show it a bunch of images with a giraffe on it, and this happens to be also in the COCO dataset, a famous benchmark dataset, and it will then find the giraffes on new pictures. But the interesting thing about transformers, we can now also zero-shot extract new objects. This means we don't have to train them. So for example, I can type in UFO, and the model will find the UFOs in the background, even though they haven't been trained. The model will also find the dinosaur, and the model will also find the helmet. All these objects have not been trained explicitly. If you like, follow the link in the lower right corner to check it out yourself. There is a demo on that. So we can also extend this to segmentation, and this can be then called zero-shot segmentation and works quite similarly. So we don't have to train all the image segmentations explicitly. In this case, I've uploaded this image of a cable cross-section, and the model automatically and without any training is able to extract the semantically meaningful areas in the image and can basically deconstruct the whole cables, the cables here. So again, this works similarly by combining the language with the images. And if you want to check this out yourself, there is again another demo. Also, I've put the publication citations in the lower, on the lower side of the slides if you want to read into this a bit more detailed. Good. So I'm not saying this is industry ready. I tried this with a few industry-specific images from the MBTech anomaly dataset. And in some cases, of course, it works. So I can extract damage from this carpet on the left side. But in other cases, it fails because in industry, we have to deal with very specific images. And these are probably not so well represented in the language data set, which these models are usually trained with. So just with examples from the internet, for example. So even I would have, without training, a hard time to identify what part of that nut in the middle is broken or wrong. And well, of course, if I have cut a cable, it's damaged already. So what's the problem with the image on the right? What I want to say is I don't think we can directly apply this, of course, to industry, but I think it opens a few interesting possibilities. So summing up, convolutional neural networks have this hierarchical understanding, and this helps them being very efficient. So we need less parameters. We need less time to calculate and inference with a convolutional neural network. On the other hand, we have transformers. They have a global understanding, but they are huge. They take much more data to be trained. They need much more time, usually, to be for an inference. But then on the other hand, they are very comprehensive. They are very, they can deal with a lot of open world problems. For example, they can also deal with multimodal data, which I've shown you. One example of multimodal is we're using two modes, language and images. And this is probably not always needed. This is probably an overkill for many industrial applications. So in industry, we can really narrow down our use cases, in many cases, I think, and efficiency is much more important for that. So the idea is that we could try and turn this thing around. So we could use our transformers as teachers, so to speak. We can use these powerful models for downstream tasks and transfer the knowledge, this very comprehensive knowledge, to neural networks, efficient architectures that can run on embedded platforms in real time. Just as an example, the IDS NXT, which we've shown here, of our host's IDS here. So this will be an interesting, I think this will be an interesting development. I think we will see, similarly as with CNNs, convolutional neural networks, before, a trend towards efficiency of smaller, of more efficient architectures. And probably convolutional neural networks will still play their part in that. So we can do this by, for example, auto-labeling training data and training neural networks for that. We can do this by distillation, several interesting concepts, which, if you're interested, I'd love to dive into that with you in research projects, for example. Just contact me. I'd be happy to see what there's to be done. And I would like to end my presentation with a little quote: "The limits of my language mean the limits of my world." I hope I could show you how we can extend the current limits of image processing by adding the power of language. And, well, there might be a second aspect to it. Probably we should still write our own text and don't limit our own world by losing the capability of writing and putting everything to ChatGPT. So thanks for that.
Thank you, Alex, for this interesting presentation. I have one question. From your point of view, do we need classical machine vision in the future anymore, or is everything AI done?
Well, I think that there will be many cases for classical rule-based image processing still, at least for the past decade, where CNNs really made huge progress. They still don't manage quite as well, cover these quantitative tasks, these tasks where you really have to measure something down to the micrometer. I think for this, you really need to have a well-controlled environment. And if you can control your environment that well, it's always good, I think, to use rule-based machine vision as well.
Okay. Are there any other questions from the audience? So I don't see really any more coming up. So again, thank you, Alex, for a nice and interesting talk. Thanks for being here.
Thanks for having me.